Nuclear notes, page 7. So just like on the previous page, how we looked at the alpha decay, let's look at the process of the beta decay. So beta decay, so that means this is the decay mode. And we need to probably go look at table O to look at possible notations for the beta particle in a reaction. So number 1, you will see it that it's the Greek letter beta, looks like a funny looking B with a superscript of a minus sign. Or you will see that it uses an E like an electron, showing a mass of 0 and a minus 1. For reaction, this is the best one because it helps us track what happens to mass number and atomic number. So carbon 14, when it falls apart because it's unstable, or when it decays, the thing that it spits out of its nucleus is that beta particle. So I'm going to place that right there. That's the bad stuff that's formed. And when that beta particle leaves the nucleus, we need to determine the new nucleus formed. So total mass on the left is 14. The beta particle takes 0 mass value with it, so the new particle must have a mass of 14. The left side shows a total of 6 protons. The beta particle affects it by minus 1, so minus 1 plus X has to equal 6. So think about how we did the example with gold 198. The new atomic number must be 7. So 7 plus minus 1 equates to 6. The new structure has a different atomic number than the original. Therefore, it's a different symbol. So if you go look on your periodic table, the new symbol is N. So this is a stable nucleus. Different number of protons, new identity. So every beta decay process will follow a similar trend to the one up above. So notice, going from your original atomic number to the new atomic number, it happens to increase by 1. Therefore, it means that the number of protons in the nucleus must increase by 1. Notice that the mass, it did not change, so it remains the same. And now we have the number of protons changed. So how did the number of neutrons change if the mass did not? So let's think about a little bit, back up. So let's think about the math here. So in carbon 14, 14 minus 6 means that there are 8 neutrons. In the nitrogen 14, you have a mass of 4 and 7 protons, so 14 minus 7 equals 7 neutrons. So the carbon 14 has more neutrons than the nitrogen 14 does. So the number of neutrons after the decay has decreased by a value of 1. And remember, protons and neutrons have approximately the same mass. So by gaining 1 proton, losing a neutron, we see no change in the total mass. The last natural decay process you need to be familiar with is the positron emission. Little copy and paste issue here. Carbon 14 does not participate in a positron emission, but calcium 37 does. So once again, we identify the decay mode. Go to your table O to help come up with the possible ways to represent the decay mode. So the positron, okay, it uses the beta symbol like the beta particle, but instead of a negative sign, a positive sign. Positron, positive. Or you will see that it's adapted where it uses an E like electron or the beta particle, mass of 0, but instead of a minus 1 atomic number, a plus 1. This is the better notation to use in the reaction so that you can track how the mass and atomic numbers are affected. So the calcium nucleus spits out the positron, so let's put down its symbol. And from there, we need to come up with the identity of the new nucleus form. So the calcium-37 is unstable. It spits out the positron emission. That's the bad or scary stuff we don't want to be overexposed to. But the positron takes 0 AMUs with it, so the new structure has a mass of 37. But we notice that the positron affects the atomic number by +1. We have a total of 20 protons on the left. So what number, this number here, +1, will add up to 20. And if we do the math carefully, it would be 19 protons. So 19 protons plus the +1 from the positron would give us 20. And if you go to your periodic table, you will see that calcium does not use an atomic number of 19. Instead, that is potassium. And potassium, in comparison to calcium, is more stable. So the summary of how, when a positron decay or emission occurs, how does the new structure compare back to the original structure? So you notice that the atomic number decreased by 1, 20 to 19. Therefore, the number of protons decreases by 1. Since atomic number and number of protons represents the exact same thing. The mass, notice that the calcium has a mass of 37. The new, more stable structure also has a mass of 37, so it remains the same. So the proton number changed, the mass is constant, so we need to figure out what happened to the number of neutrons. So if we go and do our math, 37 minus 20, okay, so 7 minus 0 is 7, 3 minus 2 is 1, so this structure has 17 neutrons. Okay, harder math here to do in my head, 37 minus 19, so 17 minus 9 gives us 8, and 2 minus 1 is 18, and so the potassium 37 has a total of 18 neutrons. So 17 versus 18, we see that there's an increase in the number of neutrons. Oops, let me rewrite this. So the number of neutrons, it increases by 1. Every positron emission process will have the same effect on the atomic number, number of protons, mass number, and neutrons.